3.4, linear recurrence relations. In this part, we will solve a special type of linear recurrence relations because this method is very general, so we can use this method to solve a large class of linear recurrence relations. All right, so let's look at the problem. Still, our Fibonacci numbers, that problem. Yeah. In this problem, we just proved. So I used 3 videos to prove this formula is correct. But now the question is, if nobody gives you this formula, how can you verify it? Right? So we need to guess the correct formula first, then we can verify it using the mathematical induction. But if nobody knows the formula, and you can see from this special form, it is very hard to guess it. Nobody can guess the formula in this way. Yeah. So now the question is, we should have some method to find it. We should have some, formal mathematical procedure to find the solution. So this video, we will do that. First, we want to, give a suitable name to the recurrence relation of this type. This type. All right. So look at this name, this long name. Okay. Second order linear homogeneous recurrence relation with constant coefficients. How long is the name? Second order, not first order, second order. Second order, yeah. So here you can see, all right, so left-hand side f of n, right-hand side 2 terms at the right-hand side. So that's why the second order. If only 1 term, the first order. Yeah. So we solved the first order before. Remember, in that the Tower of Hanoi, problem, we solved that first order linear recurrence relation. Okay. Here, the second order, linear homogeneous. What is the meaning of this homogeneous? Because here there is no constant. Fn minus 1 plus Fn minus 2, and then there is no constant. The constant part here, 0, nothing. If there is no constant term, we call it homogeneous equation. If there is a constant, non-homogeneous. Okay? The Tower of Hanoi, that linear, first order linear recurrence, that one is non-homogeneous. Non-homogeneous because we have a constant. Okay? Yeah. So remember, so that one, we can write in this way. Sorry, Cn minus 1 plus 1. Yeah. This is a non-zero constant, so it's non-homogeneous. Linear term, so you can understand because there is no square term, right? No other non-linear terms. So if I write Fn equals Fn minus 1 square, things like that, n minus 2 square, non-linear, right? Yeah, non-linear. But this one, linear function. First order linear function. Linear function, right? Yeah. Here, in general, y equals ax plus b for constant a, constant b. So this is a linear function. Yeah. Yeah. The degree of this x variable is 1. Linear term. Yeah. All right. So you can understand this long name, the meaning, why we use this long name. Yeah. All right. So now you can see the general function format in like this. B cannot be 0, because if b equals 0, then it becomes the first order homogeneous linear recurrence relation. Yeah. All right, so for our Fibonacci problem, very simple case. A equals B equals 1. Yeah. So we have this. Yeah. Now let's try to solve it. Yeah. To solve it, yeah, the next step, solving Fibonacci recurrence relation. Some of you probably still remember, actually you have solved it before. You solved it before in your Math 3000, discrete math, Math 3000, discrete math. You solved it before. There is a formal procedure. Yeah. So you can easily, get that part back from your textbook or notes. You can easily get the whole procedure back. But here, I want to go through the whole procedure. When I go through, I want to talk about some mathematical thinking, idea, and why we do in that way. So, try to inspire, your thinking, your problem solving, logical reasoning. Yeah. So that's my purpose. So not just to repeat the same thing again. So we try to look at the whole thing from a different angle. Try to get more high level understanding. Yeah. All right, so let's start. Yeah. All right, so this is the current linear homogeneous second order recurrence relation we need to solve. Okay, all right. First, now let us take a special view. Yeah. So here we look at this question. We use a very special view on it. So what kind of view? Yeah. We consider a sequence. Yeah. Because using this recurrence formula, we can generate a sequence, right? So remember, so in our original problem, we wrote 0, 1, 1, 2, 3, 5, 8, 13, right? So that sequence. Yeah. So here we represent that sequence as this AK sequence. Yeah. All right. Yeah. Now, when we look at this AK sequence, the next step, it's critical. The next step, we want to guess its structure. What is the structure of the sequence, right? Can we guess a little bit? In math problem solving, many times we need to make guess. Okay? So we had this experience before, yeah, many times. Now we need to make a good guess another time. Yeah. But here, so you may ask me, why, how do you know you need to make some suitable guess, right? How do you know you need to make suitable guess? Yeah, that's the main part. So I want to justify, the structure guess I'm making here. I want to justify it. It's not easy. Yeah, that is probably the hardest part. Yeah. All right. So here the guess is like this. Yeah. We guess the sequence. We expect the sequence take this structure, t to the kth power. So actually we call it a geometric sequence. Okay. T to the 0, t to the first, t to the second, third, and so on, the kth power. Yeah. But this looks like magic. How do you know you make the guess like this? Yeah, so here, let me justify it. Yeah. Yeah. And the first time when I saw this structure, I couldn't understand myself. Okay, it took me a long time to understand, as I explained to you right now. It took me a long time. Yeah. All right, so it's not easy. Yeah. All right. So here, let me explain why we make the guess in this way. All right. I want to go back to the first order homogeneous recurrence relation. So remember, in our Tower of Hanoi problem, we get that D sequence, right? Yeah. C sequence, but we do some transformation, we make a homogeneous, because the original linear recurrence relation is not homogeneous, but we add 1 both sides, so we get a homogeneous. So this is homogeneous. So this is the first order, right? Yeah, 1 term at the right-hand side. First order linear homogeneous recurrence relation. Okay, so that's very easy to solve, right? Yeah. Here you can see what is the solution of this one. Okay, 2 to the nth power, right? Yeah, 2 to the nth. If I write this, yeah, 2 to the nth. So in our Tower of Hanoi problem, 2 to the nth. Is this same as t to the k? Yeah, t equals 2. See, t equals 2. So at least the solution format of first order linear homogeneous recurrence relation gives us some hint. Yeah, because the geometric sequence is the right structure, okay, for first order linear homogeneous recur relation, right? Yeah. So at least that's the right structure for first order. But for second order, we don't know. It could be this one, it could be the same structure, could be different structure. We don't know. Could be the same, could be different. But does it work for second order? Does it work for second order? We don't know. We know it works for first order, but we don't know if it works for second order, right? We can try it. At least when the first time we have no information, can we try it? Can we try something that works for lower order recurrence relation? So definitely it's natural, right? Try, when we have no idea, we know something is successful before, so it is quite natural. We want to try if it works another time, right? Yeah, all right. So that's the rationale I want to give you, why we use this structure. Okay, all right. The second thing I also want to give you the idea, we call it mathematical model. Mathematical model. I don't know if you heard of that. Yeah. When we solve real world problems, many times we need to make mathematical model for our problem. So what's the mathematical model? Structure. Model means we want to use some special structure to describe our data in the problem. So we try to use the right structure to describe our data. So that structure, so we call it a mathematical model. So here we can say this geometric sequence, that is our mathematical model we use to solve this second order linear recurrence relation, homogeneous, that problem, right? Mathematical model. Yeah. So the reason I use this mathematical model view, because if you choose the right model, the model can reflect your problem well, or your problem fit your model structure well, then you can solve the problem. But it's also possible you choose the wrong model for your problem. So that's very likely. So people just choose the wrong model. If you choose the wrong model, you cannot solve it. You cannot go very far. So you just, get stuck somewhere, right? Yeah. All right. Yeah. Because here, probably some of you, you can try different model, right? Yeah. So that's very likely. Yeah. Yeah. All right. Now, let us use this model to solve this problem. Yeah. All right. The first time when we try to determine this t, because we don't know what is this t value, we can ignore the initial condition. Later we will fix it. Yeah. Initial condition is important. We need to fix it, but we will fix it later. Yeah. The first step, we don't worry about it. Yeah. So let's do our work. Yeah. Determine the t first. Yeah. All right. Now you plug in. Yeah. Here we assume a sub k equals t to the kth. So if you plug in into the original recurrence relation, you will get this equation, right? Yeah, very simple. Then you do simplification. You cancel out the term t to the k minus 2 power, both sides. So you get a simple equation, t squared equals t plus 1, and we call it characteristic equation. So this one. In your discrete math, you call it characteristic. Okay? Characteristic equation. Okay? Discrete math. Yeah. Yeah. That two solutions. So this time we get two solutions by our quadratic equation formula. Yeah. T1, T2. Plus version, minus version. Yeah. This time, we cannot ignore the minus version, okay? Yeah. Remember, in the previous time, the plus version corresponds to golden ratio phi. The second one, we drop it in our previous computation. The reason, because at that time, the negative number, this is a negative number. The negative number does not have the suitable meaning in geometry, a over b. Remember, the line segments, the ratio of line segments cannot be negative number. So we drop it. All right, so that is, the reason is the geometric meaning. But here, we don't worry about geometric meaning, right? Here, we look at the sequence, t to the k. Nobody says t cannot be negative, right? Nobody says that. T cannot. The only condition it must satisfy this equation, characteristic equation, right? Characteristic equation and that recurrence, that equation. T could be negative in an algebraic sense. No problem. Yeah, so that's why we keep also T2 version, T2 solution. Yeah. All right, so next, now we need to solve the complete problem. All right, yeah. This time we have two solutions for the characteristic equation, T1, T2, and we know both t values can satisfy the original recurrence relation. When we plug in t1, we have this version for the recurrence relation. When we plug in t2, we have this version of the recurrence relation. Both correct, right? Both correct, yeah. But the only thing, it's not good for our problem. Only thing it's not good for our problem, they do not satisfy the initial condition. All right, initial condition. Yeah. So that's the only problem. Yeah. Now it is the time to fix the initial condition. So we need to fix initial condition. Okay. So the last step, we need to fix the initial condition. Okay. All right. Yeah. So the question, how to fix it? So our view, our understanding, how to fix it. How to use two special solutions. These are two special solutions, right? So special solution 1, special solution 2. How to use these two special solutions without the initial condition, yeah? Because they do not satisfy the initial condition, yeah? Without initial condition. To get a new solution with the initial condition, right? We need to generate, we need to produce a new, different solution than these two, different, but this new one should satisfy that initial condition. So that's the last thing we need to do. Yeah. All right. Next step. Yeah. You know, which direction to go? We need to have a clear direction to go. Yeah. Which one to go? Okay? Yeah. Another question. Is there a special way to combine these two solutions to get a new solution? How to produce a new solution, right? How do you produce a new solution? A new solution should be related to old solutions, right? Yeah, because they're all solutions. They have the similar structures. They should have some relationship, right? Yeah. So we do not want to create a new solution from scratch. We have done a lot of work finding two special solutions. We don't want to throw away those two special solutions to, generate a new one from scratch. That's not good. Yeah. So our idea to generate a new solution from two special old solutions. Yeah. So next, let's do that step. Yeah. Another big important step forward. Yeah. All right. So this time, I want to introduce a new concept. So this concept, I don't know if some of you heard of this concept before. Yeah. This is a simple concept, but very basic, very useful concept. Yeah. It is called a linear combination of two variables. So linear combination concept. So what's that? Linear combination of two variables. How do we create a linear combination of two variables? Yeah. The form is this: ax plus by. Here, a and b, two constant coefficients. Yeah. So we can choose any numbers we like, but as soon as we choose two coefficients, a and b, we should fix. Yeah. X and y variables, so they can change, but the coefficients a and b never change after you determine those two constant. Yeah. All right, so that's the concept of linear combination. So very simple, but now it is very useful for our current problem. Yeah, so what's that? Yeah. So this time, with this concept, we want to take advantage of this linear, remember, what's the name of our recurrence relation, right? Second order homogeneous But there is a main keyword, linear recurrence relation, right? So our equation, linear equation, linear. So linear equation means it has this linearity property. Linearity property. So what's the linearity property, right? What is the linearity property? So here, let me explain the linearity property. Okay, all right. So any linear combination of two solutions is also a solution. Right. So we have one special solution, we have another special solution. Now we can do linear combination of these two solutions, right? Yeah, linear combination of based on the linearity property, the linear combination of two special solutions is still a solution. That's the best thing we can get from the linearity property of the linear equation. All linear equations have this property, linearity property. Right? Why we call it linear equation, right? Because they satisfy the linearity property. Here we enjoy this property, so we can get a new form of solution. What is a new form of solution? Linear combination of two old solutions. Capital A times the first solution plus capital B times second special solution. What is the A value? What is the B value? Determined by initial condition. So here you can connect to your discrete math procedure, right? Yeah. So many of you probably can recall, connect to your discrete math procedure solving the problem. But here you can see when I repeat the same procedure, I introduce a lot of new ideas, new concepts. So you can see, mathematical model, geometric sequence for the mathematical model, right? Yeah, special solution, generate new solution using linear combination, that kind of new ideas, new views. You don't have that part in your discrete math discussion, right? Yeah. All right, so let's continue. Yeah. So now the question, how to determine these two constants for the Fibonacci numbers? Our last step, determine these two numbers using the initial condition. So that part pretty simple. Yeah. So let us do that part for the final step. Now, the goal, we want to determine the constant coefficients A and B such that initial condition is satisfied. Now, let's plug in specific small n numbers. The first one, n equal to 0, we plug in, we get A0. And we know A0 equals 0. So that means capital A plus capital B equals 0. Our first equation. Yeah. Then we find B equals negative A. Simple, easy. Yeah. Then we plug in n equals 1, so we get A1 in this one. And we know A1 equals 1, right? But we replace B by negative A, and we can do the simplification. A times root 5 equals 1. So we get A value equals 1 over root 5. Then B value equals negative 1 over root 5. So we have both constant coefficients for the linear combination. So at the end, we can write the new form, right? Yeah. Yeah. All right. So the new form you can see in that way. So that's not a guess. So that's the computation result from formal standard procedure. So now, It is correct. Yeah. Yeah. Even we do not verify, it is correct. But it's good, so we use a different way to verify it. So we have more confidence in this one. Yeah. Yeah. All right, so here, after this long discussion, so I hope you can follow. Yeah. You can understand all the steps. Yeah. The most important thing is the thinking. Yeah. Why are we doing this way? Yeah. So what's the logical reasoning path? Yeah. Problem-solving path behind it. Yeah. So that will be very useful. If you can use it to solve other problems, that's the best I want to see. Yeah. All right. So we finished this video, and also we finished the whole part C of